Determination, as we know, gives out the idea of the explanatory power of the model. So it tries to explain how much is the variation in the dependent variable which is explained by the model. Now, if I take the same total sum of squares equation which we have written on the earlier slide and we divide throughout by TSS. So on the left hand side, we know it's the total sum of squares. Right? So imagine it's TSS upon TSS, and that's why we get this 1. So dividing by TSS throughout. Now from this above expression, we have R squared, which will be the first one, expected sum of squares upon total sum of squares. Now for linear regression, R squared is given by this, whereas for multiple regression, we have R squared, whereby we have dependency on Y and Y kappa. Now for linear regression, we had just one single variable, right? So that way we didn't have to worry about what would happen when we include more and more independent variables into our setup. But whenever we are talking from a multiple regression point of view, that is something which becomes very, very important, because there is generally a tendency of the model that as we provide more and more number of independent parameters, the model's R squared is expected to go up. So that is like a typical behavior for R squared. And that is something which we need to be very, very careful about. So for example, let's say you're working on a data science experiment and you have, let's say, 4 parameters which you're currently working with. You get R squared. So let's say with 4 parameters, you get R squared to be equal to maybe 70%, for example. Now, let's say we feel that there are 3 more variables which are relevant to the model, and let's say you make n equal to 7, and your R square goes out to, let's say, 80%. So just by looking at this, we may feel, yes, and the model accuracy has improved. That is, by including 3 more independent variables, it has increased the accuracy. We may perceive it this way. But that may not necessarily be the case, because as I mentioned, the tendency for R squared is to go up as it sees more and more amount of data, i.e. it has more and more number of independent variables which are coming in. So that way, just relying on R squared is dangerous. We cannot do that. So for that purpose, there is one more metric which we frequently use as a part of our analysis, which we call as adjusted R square. Why we require adjusted R square is because we want to understand that if we are increasing our number of independent parameters, let's say from 4 to 7, are those 3 new parameters really adding explanatory power to the model or not really? So for that purpose, we need an idea which we call as an adjusted R squared. So as I mentioned, to overcome the problem for R squared, which has a tendency to increase with increasing number of parameters or independent variables, we use an adjusted R squared. So this is the standard formula for adjusted R squared, where n is the number of observations and k is the number of independent variables. You'll observe that RA square is less than or equal to R squared, and this is the crux. RA squared or adjusted R square will specifically tell us whether a certain independent variable or additional independent variable coming in, is it really adding anything to the explanatory power or not? So that's what an RA square explains. So let's see that through a simple example. So imagine that there is a risk manager, and the risk manager is working on a couple of models. So let's say in the first model, the risk manager runs a regression on monthly returns, and they are using 5 independent variables. And this is over, let's say, 60 months of data. We are given the total sum of squares is 460, the residual sum of squares is 170, and R square is 63%. Now, if we have to calculate the adjusted R square, so we have RA squared using the same formula, we get this as 59.6%. Now, let's say the risk manager adds 4 more independent variables on top of it. And let's say the R squared now improves to 65%. We again calculate RA squared, we get 58.7%. So here, if you observe that by adding more number of variables, it's not really adding to the explanatory power of the model. So if it's not adding to the explanatory power to the model, then it's always better off to stick to model 1, which has fewer number of independent parameters. Because remember, this conclusion comes from the idea of having a parsimonious model. That is, we need to have parsimonious model. That is, it is better to have fewer number of independent variables as the parameters, because then tuning of the model and the overall model stability that increases drastically. So in this case, it's better off if risk manager sticks to model one